Welcome everyone to TigerBeetle, a show where we look at the TigerBeetle database, a very fun little but quite powerful database implemented in Zeek, which follows slightly unusual current practices, the so-called Tiger style. Things like never allocation memory, making everything super deterministic, and ensuring deep correctness of the code through thorough simulation testing. Let's get started, and let me try to tweak my audio setup, as I love to do at the start of every episode. Where we are at. Recently, we've finished reading through, the main storyline of TigerBeetle. We now understand more or less every piece of work every piece of technology that underpins TigerBeetle. We know what is clients, what are replicas, what are message bus, how the journal works, how the tables are laid out on disk, how object cache is used to read data from the tables, how compaction is used to compact the tables, and all this stuff. We don't yet know, every single detail in the TigerBeetle. For example, we haven't yet covered the sync algorithm, but in general, right now, you should fully understand, you should fully have it in your head, how the data moves through TigerBeetle. And last time, the plan was to just do a really long, really deep dive and to just go through the entire TigerBeetle following the path of a single transfer. Luckily for you, last time, a little emergency happened here locally, and I had to cut the episode roughly at an hour mark and continue to put out the fires. So today, and instead of one super long gigantic episode, we will get one reasonably sized episode and one super gigantic episode today. Okay, so let's get started. Let's open our middle source code, and let's see where we started at, where we finished at last time. So we have TigerBeetle, and here we have transfer, and we are looking at the path of this transfer. We learned how the transfer is first created by request in a client. Okay, and rookie mistake. Let me actually. Okay, this is much better now. Let me actually share my screen. Okay, so last time we learned how this transfer goes into the client, where client batches multiple transfers, and sends a so-called request at the primary of the cluster. So request is not a single transfer, request is a batch of 8,000 transfers. On the primary, actually, let's just go and see this. On the primary, requests get converted into a prepare, and the most important part of this conversion is the assignment of the op number. So this is where the primary makes a decision and orders this request relative to all other concurrent requests. Then this prepare in parallel is replicated to all other replicas following the ring topology and is appended to what a long function. Appended to a journal, where appended to a journal means that we write prepare to the ring of prepares, and then separately we write prepares header to the ring of headers, which allows us to recover from faults in the journal, which is out of scope for the episode. Okay, so now we've continued from this. Let's follow this prepare as it leaves the primary and arrives at a replica. Well, actually, it will go into this same on prepare function. So if we, oh dear, why it doesn't work? Pipeline primary pipeline prepare. If we look at this pipeline prepare function, we'll see that hey, actually the primary just calls this on prepare function on itself. So actually there isn't much difference between how a primary and how a backup process prepare. They both will replicate this message and they will append the message to the log. So how replication works, we understand it. We'll basically end up in some other replica calling this on prepare. So let's see how append works. Or rather, I think we've covered the body of the append last time. So we go and we write prepare, and then we send prepare OK. Where prepare OK is a message which a backup sends to the primary to confirm that it indeed received prepare with a specified checksum and it durably persisted it on its own log. So now we follow the path of this prepare OK, and as usual we are in on prepare OK method. This is again is the primary's job to count prepare OKs, and this is exactly what the primary is going to do. It is going to maintain okay, I am confusing my shortcuts here. It is going to maintain, and what is a quorum counter? Quorum counter is a bit set. Okay, so basically for every prepare, primary maintains a bit set of replicas which acknowledged this prepare. And if the primary received the quorum of prepare case, it will go and proceed with committing. So this is the essence of the replication part of the VSR protocol. In a cluster of 6 replicas, we replicate prepare to every replica, but we only wait for 3 prepare keys. Once we get a quorum of 3 prepare keys, we consider the prepare committed and proceed actually executing the operation. Now, before we go into the actual execution, into this like commit pipeline function, let's briefly cover the set path. Okay, so this is the heavy path. Client sends the primary. Client sends a request to the primary replicates the request. The primary accepts a quorum of prepare OK and proceeds with actually. Proceeds with actually committing stuff. The heavy case does not always work because the primary could die, or the primary could get partitioned from the cluster, or something else bad could happen. It might be the case that we actually, to remain available, we have to elect a new primary. So how would that happen? We won't be covering the view change protocol in detail. I believe we've actually covered this at least to some extent in like one of the first few episodes. But briefly, the idea here is that a bunch of replicas figure out that, hey, primaries are unreachable, or otherwise the cluster is stuck, and they figure out that, hey, they need to move the primaryship to some other replica. So they sent a bunch of so-called do view change messages. What is a DVC? Well, as usual, you could see all the messages in message header, the zip file. But basically, DVC is do view change, and it is just a set of recent prepares that the replica has accepted. So basically, like, to select a new primary, we need to make sure that the new primary is aware of any prepare which could have been committed. And the way we do this is that every replica just collects every recent prepare in like a single package. Well, actually, not the entire prepare, just the header of the prepare, but the header contains the checksum of the body, so that is enough. So every replica contains a bunch of recent headers and then sends this like bag of headers into a replica which is going to be a primary. Now this new prospective primary collects these bags of prepares from every backup, and looking at this like cluster-wide state, it can actually infer which prepares were committed and which prepares could be safely truncated, and safely starts a new view, maintaining all the committed messages. So update view. Okay, so the first thing to set the view change is actually to collect this set of headers, which might be headers corresponding to prepares, which might be present in the replica's journal. And this is the job of view change update headers function, where we go through all the recent headers and try to find the corresponding header in the journal, and then we either append this header to the set of headers we should send to the primary, or we append a blank header, which means that, hey, we don't have that thing. And then separately, which is actually something specific to Target. After we collect this set of headers, we also, for each header, set the so-called NAC or present bit. What does it mean? Okay, so in general, let's say you're a replica, and let's say you think that it's time to okay, before we go there is an excellent question in the chat. I know this must have been said, but which node starts the view change? This is an excellent question. This indeed has been said half a year ago, so probably it makes sense to briefly cover it. Which node starts view change? Well, the simplest algorithm is to say that, hey, any node can start view change. So if you, as a member of cluster, think that, hey, the primary is unreachable, you could just broadcast a message saying, hey, let's do view change. And then if anyone hears you saying, let's do view change, they like think and say, okay, yeah, let's do view change. And like, that way view change kind of like virally spreads around the cluster. And this is actually a pretty nice algorithm because it allows you to quickly detect when you need to do a view change. But this algorithm has a problem. Suppose that a failure is that a node is partially isolated from the cluster. Specifically, that if the node sends a message to the cluster, this message gets through, but any message directed at the node actually gets cut out by the firewall or something like that. So, like there is asymmetrical partitioning. Node can talk to the cluster, but the cluster cannot talk to the node. In this case, well, this node obviously will be considering primary to be unreachable, and it would start a view change. And because the cluster will be able to hear this node, well, the cluster will then go and proceed with view change. But this view change wouldn't actually make the primary available for that partially unreachable node. So at some point later, this partially unreachable node figure out that, hey, kind of like we still need to view change. And it will again send this view change message, and the cluster again will trigger a view change. So we'll be able to maneuver the cluster in kind of like a live log situation where one partially unreachable node disrupts the rest of the cluster. So that is why, in reality, the protocol for starting view change, well, it is also a protocol, and it requires more than one node. Specifically, this is how it works. If you, as a member of a cluster, think that it's time to do a view change. So you cannot talk to the primary, or for example, you can talk to the primary, but you also notice the clients which can talk to you and which cannot talk to the primary. Or I don't know, you can talk to the primary, but you realize that you are not receiving prepare, so like only pings go through. You think that, hey, it's time to change. It's time to elect a new primary. But you don't actually, you don't trigger view change at this point. Rather, you broadcast a suggestion to start view change. You broadcast start view change message. Let me check where. Okay, I am bad at this. Message here. Start view change. And start view change is a very, very simple message. It basically says, okay, so let's start view change. But like if a different node receives your start to change message, it's kind of like, okay, so that node wants to start to change, but well, okay. If I am able to talk to primary, I won't actually be like, starting to change. I'll be sitting there. But if the second node also considers the primary to be unreachable, it will also start broadcasting start to change. So the idea here, like, each node individually notifies the cluster that, hey, from my perspective, I think the primary is unreachable. And only when you have a quorum of those start view change messages, when you see that a majority of the cluster considers the primary to be unreachable, then they figure out that, okay, at this point, we are going to send a do view change message. And do view change message actually triggers the view change. So if any other replica receives a do view change message, it immediately transitions to the view change. So yeah, that's the answer to the question. Each node individually decides when it should start view change. And if we get a quorum of nodes which think that it is a good idea to start view change gets started. And another important thing, from a consensus perspective, what does it mean to start view change? It doesn't mean that we transition to a new view because, well, new view might not actually start. Like you need to work in primary, but it definitely means that the old view is finished. So no more commits can happen in the old view. So that is why when during do view change, replicas send a bag of their local headers to the primary, they kind of like also implicitly guarantee to the primary that they aren't going to accept any new headers in the view which has just elapsed, which allows the primary to correctly infer which stuff is and isn't committed. Okay, so going back to do view change and set NAC and present bits. Okay, so imagine you're a replica in a cluster, and there is like some op number like 92. What are possible cases for this op number? Well, the most likely case is that you have this header and you have this prepare and everything is okay. So in this case, you kind of like send this header and you set present as true for this prepare, saying like, yes, I have this header. I can provide it for the cluster. What else could be? It could be the case that you don't have this header at all. So like, your highest op which you have ever accepted is like op number 10. And like, obviously you kind of like didn't accept op number 92. And in this case, what you're saying to the cluster is that, hey cluster, I don't have this header. And moreover, I'm pretty sure that never ever I had previously accepted this header, this prepare. And that's like kind of like, clear-cut cases. Either you have it or you don't have it. But there is like, gray area cases. Like suppose you're a replica and you're restarting from a crash. And then there is corruption in your journal. So you try to prepare and there is a checksum mismatch. And now, like, you like definitely don't have this prepare. So there is a checksum mismatch. But you kind of like, you might or might not have this prepare in the past. So in that place on disk where you would have written prepare 92, you get a checksum mismatch. And that means that either in the past you did write prepare number 92 there, and this prepare 92 got corrupted. So in the past you did arc this prepare. Or it might be the case that what's written there is actually prepare number 10. And kind of like while it is still corrupted, you still can be sure that you have never ever accepted this prepare number 92. So that's why we kind of like, besides just having or not having this prepare, the replicas explicitly say where they can not acknowledge, where they can guarantee that they have never ever and will never ever send a prepare okay for that prepare in a particular view. Okay, so so eventually, the whole pack of DVC messages gets to the primary. And the primary doesn't need like, DVC message from every single cluster member, well, because that would trivially make the cluster unavailable, but it does require DVC message from majority of the cluster. And now, with all of these messages, the primary could actually go and decide which messages get into new view and which can be safely truncated. So specifically for each prospective message, the primary counts how many replicas knocked this message and how many replicas said that they have this message. And the logic here is basically that if we have a copy of the message, well, that's good. We can just accept it. If we don't have a copy of this message, we additionally look at the NACs. And like, if, okay, so let's work through an example. Let's say we are in a cluster of 6 replicas. So our view change quorum is 4 and our replication quorum is 3. And you are a prospective primary. And you have received DVCs from 5 replicas out of 6 in the quorum. And among those DVCs, there are 4 necks for a particular prepare. Well, because there are 4 necks for this prepare, you know that there could be at most 6 minus 4, at most 2 prepare OKs for this prepare. But 2 is less than 3, very hard mathematical fact, and that means that you could be sure that, hey, actually this prepare is not committed. And in that case, it would actually be safe to go and truncate this prepare. So that's it. The specific mathematics and specific conditions like behind this algorithm are like slightly tricky. Like it is not easy code, very much not easy. In some sense, even even much harder than like compaction, which we've slogged through during the like 5 or 6 episodes. But the bottom line here is that the primary, the currently prospective primary, given enough DVC messages, could actually compute the correct state of a new view, and then it can start a new view. So that is how we achieve liveness in the presence of false. Okay, so let me just take a sip of tea, and then we'll get back to the commit path. Okay, perfect. Back to the commit path. It was, I think, primary commit pipeline. Yeah, so we as a primary, again, we have the primary here. We as a primary have accepted the prepare OK, which flipped us over the quorum threshold for a particular prepare. So we now will go and commit to prepare. And we'll go into this commit function. Is the high level function, like the high level commit loop. So let me explain this. Well, first of all, we did cover commit path before, but it was somewhat heavily refactored since then, so this code is new. So we'll probably take a slightly closer look here. Okay, so what this code actually does is basically just calling this whole bunch of functions just one after another. And now you people like to complain like how like async Rust is like super complicated. So now you will grow to really appreciate this. So commit replace a tab, commit execute. I am not good with my keyboard today. Okay, this was commit execute, and then we have commit compact and commit checkpoint data and checkpoint superblock. Okay, can I? Okay, I think I could actually make use of advanced editing technology here and do this, and this. Okay, not this far. Oh dear. I'm very bad with keyboard today. Okay, hopefully. Okay, so. And actually here, okay, this is not exactly Rust. So let's say this is while true. If self commit prepare equals now. Okay, so this is like the logical flow of things during commit. Well, first of all, there is a loop because we also have pipelining. Like, when like primary accepts prepare, like, it needs to replicate it, needs to wait for prepare case, like, there's like a lot of waiting. And like, why just wait there, sitting and twiddling your thumbs while you could do something else? So the way this actually works is that primary, like, accepts just a whole bunch of requests and replicate and converts them to prepares and replicates prepares, and it commits only when it receives a quorum of prepare case. And this actually means that, like, you might receive quorums in their own order. So for example, you could have like 3 prepares outstanding, and you first receive a quorum for the second one, then for the third one, and the first prepare is actually the last one for which you receive the quorum. So by the time you receive the quorum for the first prepare, you actually could, like, commit the whole, the entire train of 3 prepares. Because, well, obviously you need to commit stuff in order, because the main thing, like the purpose here, is actually to just order every single individual transfer against each other. So that's why we have like this loop here, which should commit everything that we can commit right now. So it should execute everything which has a quorum of prepare case. So how do we do this? Well, first of all, we check if there is a prepare for which we have a quorum of prepare case, and if it's not the case, we break out of the loop. Then we go and run prefetch. So prefetch is like disk.io. Then we do reply setup, which is, well, let me say, not important. We'll cover it later, but not today. Then we actually, like, run transactions. CPU work for double entry book keeping. Is it true that in the word book keeping you have triple of double letters in a row? I've never really realized that, and well, this is really something. Kind of like cellar door kind of awesomeness, or like, the how was it called? Yeah, cow crown thing. Okay. Basically, we did the CPU work for actual double entry bookkeeping, and then we do like our favorite compaction. And spoiler, while we were spending like 5 episodes on compaction, I was like, kind of like saying, hey, I will rewrite this. So bad news, I did rewrite this. So probably in the next episode, we'll go back to the compaction and see the new implementation. Okay, so like we do compaction, and then we do like checkpoint, where compaction is optimizing the, compaction is essentially garbage collection of the data on disk. And the checkpoint is a process where we swap the root pointer for the data on disk. Okay, and that's it. The problem is that, every function here is actually asynchronous. Everything here does some amount of input-output, well, except this commit execute path. So what this actually looks like is like commit start.await, and then commit prefetch.await, and then commit reply setup await, and then await, and await, and await, and await. But, well, Zig currently kind of doesn't have async await, and even if Zig did have async await, it's not completely clear that we would have used it. So, okay, like your language doesn't have async await. How do you do this manually? And well, kind of like, the idea is like, yeah, let's just do this yourself. Let's say that our compaction. Let's say that our compaction actually returns something like enum. Actually, why do we need to? Okay, it's pendant. Pendant's not interesting. Okay, commit reply setup. That function which I didn't want to talk about, but well, let's use it as example. Okay, so let's say this returns enum of like pendant or ready. And the idea here, when you run this function the first time, it schedules some asynchronous work to actually get the things done, and then it returns pendant. And okay, no, actually this is slightly confusing. So okay, this is actually worse. So this function might or might not be asynchronous. It might need to do some disk I/O, or it might be the case that the stuff is already in memory. So the semantics here is that you call this function, and if it did the work immediately, it didn't do any I/O, it returns ready. But if some asynchronously is involved, if this ended up issuing a write syscall through IO uring with the corresponding callback, this function returns pendant. And the idea here is that when we return pendant, so we say if this thing returns pendant, we are going to just return from this function, and let the callback call this commit dispatch back. So when we are called back, we need to jump into the middle of this structure. So we called commit reply setup. This scheduled some asynchronous work. Then some asynchronous work got done. We are back in this function, and then we should continue. We shouldn't be executing like this line. We should continue here. So okay, if this was C, that would have been a Duff's device that bought all the jokes. So we'd have in C, we would have some kind of switch state, and we would have here something like commit start, and commit prefetch, and commit replies setup, and execute, and then here, so we would say something if this is pendant. Well, actually, no. This is okay. So this is in C. Okay, C is really weird language where it would be like this. So you have the switch outside and the loop inside, and if you're pendant, you set the state. Okay, switch. We set the state to commit execute. And then we break, and the next time, we get into the switch, we jump right here to this prone, and then, there is fall through, so we continue executing, essentially, we continue executing this loop from the middle. C is excellent language. Luckily, we don't use C, so we have to recreate this struct without any kinds of go-to or cases interspersed with while loops in a super weird way. But yeah, basically this is what we're going to code. We're going to have this commit stage state variable, which says which part of this loop we should jump into. And we start in the idle state. And okay, if we are in the idle, we should start commit. So we go and set the stage to start, and then run this commit start function, which might return ready or might return pending. Why this might return pending? Well, if we have to fetch the prepare from the hard drive. So we are the primary, this is going to return ready, so it will complete synchronously. Because the primary could just set this commit prepare to the latest message if the quorum is received. Okay, so we start now we have commit stage equals start, and we also have commit prepare. Well, kind of like the semantics here is that there is nothing to commit, then the commit prepare will be set to null and will break here. Otherwise, it will be not null. So, okay, assert here. Now, okay. And again, so we were in the start stage, then we transition to the check prepare stage. Now, if we are in the check prepare stage, we are going to transition to prefetch state. And then we will run prefetch. Again, if prefetch okay, so I realized that I haven't properly explained how this all loops back. So let's quickly look at the overall structure of prefetch. Okay, so we kind of do stuff. The main thing that we invoke a synchronous operation of prefetch, which will do disk.io, and we'll pass a callback to this operation. So this callback will call commit dispatch resume, which will call commit dispatch, which will get us into this same loop. And here, we set the state to prefetch here. So when we return back to this loop, the state is still prefetch. So this if returns false and we don't execute it. This if returns false and we don't execute it. This if returns false and we don't execute it. But this one returns true. And then we continue with reply setup. So the same story here. We're not covering reply setup today. Then we are going to call commit execute, and this one is synchronous. So you see, we don't really check if commit execute is equal pending, because it is always synchronous. And then we compact checkpoint. So basically what we have explained. And yeah, this is exactly the kind of code that the Rust compiler generates for you when you write a bunch of async awaits inside the loop. And if you don't have that, well, this is kind of annoying, but not really that huge of a deal. You could go and write this state machine manager, which is not really pleasant, but well, kind of you don't have that many complicated state machines. Basically, this one and the compaction one. Well, maybe the query one as well. Okay, so now that we understand the high-level structure of this loop, let's actually go right into every specific operation. Okay, commit start. Two cases. Commits, either primary or a backup could be committed. We'll cover just the primary case. So this is commit start pipeline, and commit start pipeline means that we pop the next prepare from the pipeline. Remember, we have multiple prepares implied. And then we check whether we have quorum. If we don't have quorum, then we should really assert that commit prepare is null here, because this is like, okay, not ascendant timestamps, not really assert. Kind of like you might say, hey, here we are asserting the same thing, like, do we need this assert? It kind of like is duplicated. No, we definitely need this assert, because we assert different semantic things. Here we assert a precondition. So the precondition is, and by the way, here, I believe we also should be asserting this. Okay, so here we assert a precondition. So when you call this function commit prepare is null, and the job of this function is to set the commit prepare. Here, well, actually, maybe the better way to write this is to say something like self commit prepare equals null here and here, which is kind of like no op, but it makes the semantics clear. So it's kind of like we don't rely on the fact that, like, commit prepare is like null. Accidentally is that we kind of like really saying, hey, yes, we are finishing this function, and yes, commit prepare here intentionally should be null. Or if we actually have a prepare and this prepare actually have a quorum, then this would be a non-null. Okay, so with did commit start, now we are in the stage start. Now stage check prepare. So if check prepare is null, then we break out of this loop completely and kind of like stop our commit loop. That's the end of it. We reset everything to false. Otherwise, okay, prefetch. So remember, the big idea of Targetable, we want to run transactions as if they are running sequentially, and because running transactions, specifically financial transfers, is a highly contained workload, the fastest way we could run them as if they are running sequentially is, surprise, surprise, to run them sequentially, to have a single core which goes and executes every transfer one by one. And the performance trick that we run the actual execution sequentially does not imply that everything else runs sequentially. Crucially, we can't parallelize input-output. Specifically, always think in batches. We have a whole batch of transfers, and we need to execute it. What does executing a single transfer entails? Well, it means that we fetch debit account balance, credit account balance, check that they do not overflow, update both balances, and write both results to disk. And this is the thing. If you have a batch of 8,000 transfers, you could actually go and prefetch balances for all 16,000 of accounts at the same time. 16 because we have 8,000 transfers, and each transfer can touch 2 different accounts. So that is the job of a prefetch function. The job of a prefetch function is to go and in parallel fetch all the prepares from disk. And okay, we have some operations which are resolved by the VSR implementation itself, and for those we actually don't need to do any prefetch job. So for those we return ready here, and we'll just fall through to the next part of our commit dispatch loop. But for a normal case, I will go into state machine and call prefetch. So let's do that. Let's go into the state machine and call prefetch. Okay, state machine and prefetch. Okay, so yeah, this is a synchronous separation. We have a callback which we should call when the prefetch is done, and then we have the input, like what like the bytes with actual stuff. Okay, so here we are looking at the create transfers operation, so the basic thing which goes through target. So we cast our input bytes to a slice of transfers and call prefetch create transfers. And well, this one is kind of like, okay, I am lost. Like prefetch transfer is kind of like not interesting. It prefetches just like the transfers themselves to check for duplicate transfers. So once we've done that, we call prefetch transfers callback, and this is more interesting. So this actually, like prefetches the accounts. So we iterate over all our input transfers, and for every transfer, we prefetch 2 accounts which are touched by this transfer. So let me split my screen here. Okay, it didn't work. Let me try again. Okay, now, and let's see how this works in the Grove. Okay, I am very bad here. Okay, so again, the idea is that, like, always think in batches. Like, never ever do something with a single thing. Always like process batches of things. So that's why, like, here we don't actually go and prefetch a single account. What we actually do is that we kind of like enqueue all the IDs IDs of all the objects that needs prefetching into a single kind of like queue, and then we go and prefetch them all. So let me see here how this works. Fetch and queue, and I kind of like realize that this is not actually entirely correct as of right now. So okay, so kind of like the thing we are going to populate here is prefetch cache, where prefetch keys, is just essentially no, I don't want to go here. Okay, I've lost my prefetch keys. Prefetch keys. This is essentially like it is a hash map because it contains some auxiliary information, but like loosely it is a set of the keys we actually need to fetch from disk. Like that's like kind of like fetch from disk is an important qualification because actually we have a bunch of caches in Target. And if the data is already cached, then we actually don't have to go and prefetch it from disk. So in the Grove, let's see prefetch and queue. Yeah, so in prefetch and queue, we have a queue. And if this thing is already cached in an object cache, we return it. Otherwise, we try to look up. Okay, so this time I realized that I kind of like need to refresh the cache about the caches. So how caches in Target works? Well, the simplest one is object cache. So this thing caches transfers and accounts, the actual objects. So like, like for a given account ID, you in the cache, you have account objects, which has balances for the account. So that is simple. And if we have like, the object and the object key, then okay, it's prefetched and we return. Otherwise, we also have like, the page cache for the underlying LSM data on disk. And it might be the case that while the object itself is not in the object cache, the underlying data for the object is still in memory. So we also will go and prefetch this thing from levels. I guess. Okay, so let's kind of like, for now, just put that onto the stack of things we need to cover. Like, okay, how do we prefetch from in memory? How do we prefetch object in memory cache? Anyway, so if object is not in the cache, then we go and add it to the prefetch keys to be prefetched later. So now we actually go and call prefetch on the growths. And this actually does, like, does the actual parallel IO work. So we have a certain number of prefetch workers here, which will be in parallel fetching the next object to prefetch and doing the lookup. So I probably don't want to dive deep into how we actually parallelize this thing, because it's again kind of like nesty loop. But this is interesting. So how we do the actual lookup? Well, we go to the tree and call the lookup function. And like this worker stuff basically means that we kind of like do this in parallel for all the objects we want to prefetch. So okay, how lookup works? And again, we have several flavors of function. We have lookup from levels storage and lookup from levels cached. So we first go into the storage, which kind of like explains how it works, and then we'll go back to the cache, which will finally explain that thing which we've put onto our stack before about the cache. Okay, so we want to look up a particular key in a particular oh dear, remember how I said to you that we should always think in batches? Well, I think this thing here doesn't think in batches. I think this is wrong. Like, you see, like here we take just a single key, and that is kind of like feels wrong, because, well, kind of like can we like, take keys here and like look up, like, the entire key range into our in our LSM tree. So like, like there's like key min, key max, and then like, you get like all the levels. But well, at least looking up a single key should be easier to explain. And well, again, this is not optimal code. The architecture here is like really nice, but the current Deepin architecture is kind of like the first version that works. So there is like a lot of performance engineering which still has to get into Tagabitl to really get it to performance, which it could in theory achieve. Okay, so basically we want to look up the key in LSM level. The first thing is to find the tables which could contain this key. And important piece of information about Tagabitl, that the information about all the tables is in memory. So recap. Basic structure on disk is a grid of blocks. So a block is like 1 megabyte of 1 megabyte, half a megabyte. A block is half a megabyte of stuff, and everything which exists in Trackbital on disk is arranged in the blocks. In particular, the tables are arranged in the block. So what is a table? A table is a sorted array of values, and it is a two-level structure. There are values blocks, which are literally just a sorted array of values encoded in a single grid block. And then there is, then we take a bunch of value blocks, which are like properly sorted. So not only a single block is sorted, but any two blocks are correctly ordered. All the values from one block are smaller than all the values from the second block. So we take a bunch of blocks, and then we encode pointers to the array of pointers to those blocks into the so-called index block. Well, what is a pointer to a block? Remember, block exists on disk. So a pointer is like index of a block, and because this is disk, we use U64, not usize. So this is U64, but this is also a checksum. So disk pointer is a pair of like a checksum and address, and an array of those pointers is an index block. And index block plus all the value blocks referenced from this index block is a table. And we store meta information about the table in memory. So for every table, we store its minimum key, maximum key, address of the index block, and the checksum of the index block, which is like some non-trivial amount of bytes. But given that the index block is 1 megabyte, and it is chock full of pointers to other 1 megabyte value blocks, actually, like, I don't know what is like the size of the single table, but it's like in megabytes, maybe even like hundreds of megabytes. So like tables are pretty chunky, and you store only a small amount of that in memory. So this is like, you know, this is memory hierarchy. We use a small number of bytes in memory to address a larger number of bytes on disk. Okay. So those tables are arranged in levels, and the rule here is that when we are looking up for a key, we should be checking all the layers sequentially and stop at the first layer that fits. And this is exactly what manifest lookup gives us. It iterates all the layers, and in each layer it tries to find the table which contains the given key. Like how the layers are stored in memory. Well, again, a layer is a bunch of tables. The tables in a layer also have to be disjoint, and they also are just sorted array. So it's like binary searches all the way down there. And okay, so if this time we'll have to stop because my electricity goes out, we'll still continue next time. Okay. We go and look up. Yeah, so we go and record all the tables we need to look up. And then we go and read the index block of the first table which we need. And now that we have this index block, we go and binary search our key in that index block. And if there is no match, then we'll go to the next level and we'll go and read the next index block. Otherwise, if there is a match, then we know which data block contains this key. So we go and read the data block. And when the data block is read, we go and binary search in this data block for our given key. And if we found that, then yeah, kind of like this is the key we're looking for. And if we didn't find it, well, then it's kind of like too bad. But well, there is no such key in this table. Okay, so this was lookup from storage. We also have lookup from cache, because, like, in those functions we have just looked at, we always go to read data from disk, but data could also be in cache, in which case, like, the function is actually synchronous. So you see, in the lookup from levels storage, we okay, it's not actually visible in the interface, but here we are passing the callback, so it returns void. When it is done, it will call the callback. But in lookup from levels cache, we don't pass a callback. We immediately return the result, which might be like, hey, we found value. Hey, we can definitely show that the value is not there, or we could say, hey, I don't know, maybe the value is there, maybe the value is not there, but at least start from this level. Okay, so lookup from levels cache is basically the same thing as lookups from disk, except that we substitute synchronous reads from cache for asynchronous reads from disk. Okay, so we try to get an index block from cache, and if it is not cached, we say, okay, we don't know. But if it is cached, then we go and find the corresponding value blocks, and then we look up the value block in the cache. And again, if it is in the cache, then okay, that's our data. If it's not in cache, then it is done. And okay, so wait, I think I'm missing something. So here we read the index block. Okay. Okay, so this is cache data block search. This thing first reads a block from cache, and then if the block is actually in the cache, then we go and return go and actually binary search in the table. So okay, this kind of like concludes our prefetch walkthrough. So first we kind of like try to prefetch using in-memory data. When it fails, we do a bunch of asynchronous input-output to read the data from the LSM tree from disk, and eventually the invariant we get in the end is that everything's in the object cache. So after we have executed the prefetch, we know that, okay, now everything is in this one giant in-memory hash table. And we get back to replica to our commit dispatch. So we were the prefetch, and we started the synchronous prefetch, and that's like, was running for a time, and then it called us back with commit prefetch callback, and that called the commit dispatch resume, and that gets back into commit dispatch, and we were in the prefetch stage. We set to the client reply setup stage, which is another some bit of auxiliary asynchronous work we are not covering here. And then we are going to execute stage. And if the stage is execute, okay, I'm not, where? Okay. Okay, yeah, okay. We go to the, deleted this line, and I was looking for it. So we go to the commit execute, and in commit execute, we actually go and, well, execute our transactions, which I don't understand what we do here, but the main thing is that, okay, no, I really don't understand what's happening here. Where is actually, okay, oh yeah, that's the first line. So this is like, this is like the stuff we do like after we have executed the op. So the interesting thing here like is execute the op, like the actual work of doing things after we have done all the required input output. So here we go and say somewhere state machine commit, which should really be renamed to execute, because execute is better name there. Because commit is the logical operation of saying that, hey, this data is considered part of a state. But you can commit the data logically way before you actually physically execute the relevant state machine operations. Okay, so we go back to the state machine and we go to execute, which has basically the same signature. Well, it has a different signature than prefetch. So in prefetch, okay, let's see this side by side because it is going to be useful. In prefetch, we have an input, but for the output, we have a callback because prefetch is asynchronous. For execute, we have input and we have output. We don't have a callback because execute is synchronous. And that is like, this is the reason why TigerBeetle is so fast. It is so fast because we managed to make our sequential execution a synchronous function which doesn't have to do any kind of I/O. Okay, and execute is actually like, boring, like just double entry bookkeeping for each account, just like for each transfer, just like, check a bunch of stuff. Then fetch debit account, then fetch credit account, then and then scroll through like 1,000 lines of code of like error handling, then check that you actually can add amounts to the corresponding sides of the ledgers for the debit and credit account. If not, you return error. Otherwise, then like, hey, you like actually go and update the amounts. And like notify the LSM tree that, hey, this data is updated, and that's basically it. So kind of like just very short CPU loop, and that's it for update. Well, except for like, hey, what is like, how do we actually update the LSM tree? Well, let's go back to our growth update. So we have update. We have old object and we have a new object. Why do we need both objects? Because we also have indexes. And to correctly update indexes, you actually need to know both old and new objects. Like this is like, like understanding why we need two arguments there and how exactly we update indexes is the key thing to understand how a relational database works. That like relational database is nothing more than a DSL on top of a sorted array. It's kind of, like when you look at the SQL, it kind of like feels like there should be like, a lot of like very complicated special cases to handle SQL. But actually, if you think about it, that like sorted array is like the single data structure that you like really use. Like, this like data structure, the first data structure which you learned when you were like learning programming is actually what underpins all the relational databases. Okay. Well, of course, like it's slightly more complicated, but the basic is there. Okay, so how do we update value? Okay, where's okay, yeah, so kind of like this is the code for the index updates, and like basically we save it for each index tree. We kind of like remove the old pair of like ID and value and insert the new pair of ID and value. So kind of like let's say okay, so let's say we have like balance index and we update account ID 92 from like this amount of money to like this amount of money. So how do we do this? You do this by like remove and then insert. And like, to do this remove, you need to have this old value, and that's kind of the essence of indexes. So yeah, this is it. So now we have to update the actual stuff. And well, the objects cache is simple. Well, it is just in-memory hash map. Well, how do you update in-memory hash map? Well, just go and update in-memory hash map. Well, objects cache. Objects is actually the LSM tree, and updating LSM tree is kind of like, it's slightly complicated. But the start of the update is like there is the way updates work in LSM tree is that, like, repeat after me at this point, everything is batched. So instead of like going and updating a single value on disk, what LSM does is that it accumulates a bunch of updates in an in-memory buffer and then goes and writes this in-memory buffer to disk in one go. So in-memory buffer is just a stupid, simple array of values. And when we insert something into LSM tree, we just go and append this value to this slice of values, and that's really why it is not working as I want it to work. And that's really it for the update, because all the actual fun, interesting stuff happens, as we know, during compaction. And I think this is roughly what we are to switch to next. So, okay, yeah, kind of like we commit, execute, finished. So we are back in the replica. We are back. We've just done this thing. So after this, all the updates are in our in-memory cache. And for each LSM tree, there is a bunch of updates in the values array. So then we go and do our favorite topic. We do compaction. And this goes to state machine compact. And that goes to forest compact. And that is like hugely complicated thing. Okay, so how does this work? Okay, so that thing, like you saw in the mutable table, that array of values is, well, the so-called mutable table. And like, remember what I was saying that, hey, kind of like a table is an index block and a bunch of values blocks. Well, this like mutable table, this array of values is like really, really long. And it encompasses like as a single in-memory contiguous array, this entire thing on disk with index block and multiple values block. So now the process of compaction is that we just write this whole thing to disk now as a table. So we need to slice this single array into individual value blocks. And then we add this to the zeroth layer of our LSM tree. But the zeroth layer of our LSM tree is limited. It can contain only 16 tables. So if it already has 16 tables, then we need, before we can add a new table to level 0, we actually need to take one of the tables which are already there and push it down one level. Push it down to level number 1. And again, there's like two problems here. One is that, well, okay, level 1 could also be full. It could contain, level 1 could contain 16 times 16, so 256 tables top, and it could have exactly 256 tables. So if that is the case, then we need to take one table from level 1 and push it down to level 2. And all the way up to, like, level 6. Given that each level is 16 times larger than the previous one, well, at some point we will hit a level which contains free space. But there is a second problem. Remember, blocks in a single table must be properly sorted within the blocks and across the blocks. The same is true for tables in a level. Each table in a level is sorted, but also tables are sorted relatively to each other. If you take two tables from the same level, then all the keys in one table have to be smaller than all the keys from the other table. And if you want to move one table from level 0 to level 1, then you actually don't have this property. If you just append this to level 1, well, you will have some intersection. So this is where the merge operation of compaction comes from. When you push a table from one level to the next level, what you should actually be doing is that you should compute the full set of tables on the level below, which intersects the table which you want to push through. Then you need to concurrently read table from level A and table from level B, and you need to merge the two streams of values, and you need to write output tables as you go. So you essentially, you overwrite the data as you go. Okay, so this is compaction. Now, the hard thing here is that, you kind of you don't want to do all the compaction in the last moment. You don't want to be in a situation where you want to push something to level 0, but level 0 is full, so you want to push something to level 1, but level 1 is also full, so you want to push something from level 1 to level 2, and level 2 is also full, and you realize that you need to do a lot of work. So what we actually do is that we proactively compact things. We always try to make sure that, hey, there is at least one empty spot in every table, and we start compacting the table not when we need to push something into this table, but actually just when it becomes full. And the second thing is that, even an individual compaction is actually a lot of work, because tables are big, and a single table could intersect multiple tables on level B. So you actually, you might have to do quite a bit of work. So we actually, want to spread out compaction work across multiple requests. So when we call this compact thing from the replica, it's not hey, do all the compaction that you have to do. No, it is do some fraction of compaction. So compaction process itself is going to be paused and resumed. And okay, so I wouldn't be covering the control loop for compaction because we've already spent many episodes on this, and we'll spend the next episode on that. But I will kind of quickly run through the guts of compaction. So what do we need? What do we need to do compaction? Well, first of all, we need to figure out which compactions we even which table, whether compaction is at all needed and which tables we're going to compact. So we go and say, hey, manifest, again, reminder, manifest contains the full in-memory set of all the tables we have. Not the actual data of the tables, but metadata about the tables, the addresses and the checksums of their input blocks. So okay, we go to this manifest and say, hey, manifest. So here is this level you have, and if it is full, then please give me a table which should be moved to the next level, and all the tables it intersects with. So manifest could return null, which means that, hey, actually there's no need for compaction right now, or it could return you a table on the level and a range of tables on the level below, and say, hey, kind of like, please read this and merge them and write them as write the resulting data as a set of new tables. So okay, and then we go and we say, okay, yeah, let's start reading this. Let's like go and read the index block, and once we've read the index block, then we go and for each value block, we'll go and read value block, and then we kind of like be like working essentially with iterators. So we have iterator of like tables and values from level A, and we have iterator from tables and values from level B. And we'll go and okay, where it is. Okay, and we'll kind of like go and look at the current value table which we are merging, and we'll like slice the values which we haven't merged and say, hey, okay, so this is like the slice of values from level A we need to merge. And then we'll do the same for level B. We take like, the current block from level B and slice it according to our cursor position. And yeah, kind of like when you think of compaction, another like important intuition here is that you don't actually have to think about the tables. You could think just about value blocks, because like, well, yeah, on level B you have a bunch of tables, but the tables are sorted relative to each other. So you could pretend that this is just like one giant table with a lot of value blocks. And essentially you have a bunch of chunks on level A, a bunch of chunks of level B. Each chunk contains a bunch of values, and you need to merge everything. So you take the first chunk from level A, the first chunk from level B, and you say, okay, now let's merge this. And then yeah, just like you go and literally just like run this merge from the merge sort, like something like, you've learned arrays on your like first lesson for programming. Well, merge is like, I don't know, the fourth lesson, the third, like it's very, very, very like early, very simple computer science, but yeah, it's kind of like nice and beautiful, like simple things are usually what you need. Okay, so kind of like, you take a value from level A, level from value B, you kind of like compare them, and if it is a class, then you take one of them. If this is greater, you take the other one, and if the values are equal, you remember that, hey, this is LSM tree, and in LSM tree we have a rule that values from the lower levels have precedence over values from the levels below. So if that is the case, then we throw one value away and pick only the value that we need. Okay. The value we write, we accumulate in so-called table builder. So table builder. I mean, like, you could write Java in any language, like, Zig, async await, callbacks, still there is a use for builders. Okay, table builder. The goal of table builder is like, to like incrementally build a table. So there is like this data block which points to a slice of memory which will eventually become a data block on disk. And our merge actually, like, fills this data block. And when it is full, we call data block finish, which will compute the checksum of this block write this checksum to the header and then checksum the header itself. So like after this, like, you know, the block is essentially frozen because, well, we have a checksum. And then it will append this to the index block because like the table builder also has like this index block. So no, once the index block finish. Once the index block is full, we like do the same thing with the index block. We fill the remaining of the header fields, we set the checksum, and well, the block is finished. And then in the compaction, we are going to write the index and the value blocks, like just write and then call callbacks. And again, like the details of like when exactly we do this are like very tricky, but basically the idea is that, like, you know, we kind of like spread this work across a bunch of ops. Okay, so when you, like, you know, write the table to disk, you also want to write it to the manifest at some point. Like you want your in-memory structure to be consistent with structure on disk. So the first, the way this actually works is that we first just buffer those cases in memory. So we kind of like, we don't immediately make new tables available. Compaction sounds destructively. That hey, like you read tables from level A, you read tables from level B, and like you overwrite them. But actually, it is not destructive. You have written a new table, which is a merge of the previous tables, but the previous tables are still there. And while you are running the merge, the LSM continues to use old tables for lookups. So that's why, like, you know, you actually want to atomically remove all the old tables and insert the new tables. And this happens in apply to the manifest, where we go through like our accumulated table changes and ask our manifest to insert or remove tables. But again, this is like, for now, like, the crucial thing is that we haven't updated the root pointer on disk. Let me grab one more bit of tea. Okay, so we haven't yet updated our root pointers on disk. So although our in-memory data structure points to the new set of tables, if at this point we crash and restart, we'll restart with our old state of data on disk, which is again not a problem because nothing is destructive and everything is deterministic. So although we will redo some work, the results are guaranteed to be exactly the same. Okay, so this means that like, you know, here we'll, like, you know, run this compact. Compact will do like some amount of work I was just talking about, and then we'll like run this checkpoint thing. And the checkpoint thing is interesting. The checkpoint thing is that we have where we take all the changes accumulated so far and actually write them to disk and make them durable. So if we crash after the checkpoint, then we won't have to redo the work. Okay, so the most interesting thing here is the grid checkpoint, and the most interesting thing about the grid checkpoint is blocks missing checkpoint. Why we are checkpointing missing blocks? This is what's even missing blocks? Okay, I'm okay. I'm actually surprised that we are. Or does it just? Okay. Okay, so I think it actually doesn't checkpoint. This is just like waits for IO to finish or something like that. So anyway, probably not as interesting. The main thing is like checkpoint and the free set. So like when we create new blocks, new tables during compaction, we need to allocate some specific place on disk, and like ideally, we shouldn't. Well, we could always just literally append stuff to disk, but at some point we also release the tables, and it would be good if we could reuse the tables which we have previously freed. And this works like in a really stupid way. We just maintain in memory a full bit set of allocated blocks on grid. Again, this is where you think about memory hierarchy, where you think about how you could address a lot of memory on disk using just a few bytes in RAM. And the thing here is that one bit in a free set addresses the entire block on disk, and one bit is one bit, and one block is half a megabyte. So this is like pretty significant amplification. So anyway, you maintain this bit set, and obviously when checkpoint arrives, you need to store. You need to persist this data so that after the checkpoint, if you crash and restart, you actually know which blocks are free. So this is what happens in this freeset checkpoint call. We just go and write freeset to disk. And again, this is super simple, super straightforward. So we encode freeset as a compressed bit set, and then we write out that compressed bit set to some grid block. And in the end, we get an address and a checksum of the grid block which contains the free set. So that was checkpoint. That was checkpoint data, which is okay. I am slightly lost here. I am still slightly lost here. Well, okay. I think that's not the entirety of checkpoint data. So or maybe it is. Well, let's see. Let's see what we do in the checkpoint superblock, because checkpoint superblock is the thing which actually updates the root pointer, because the superblock is the root pointer. So okay, what do we do here? Okay. Yeah, so this is like where we write the new root pointer, and this in particular where we write where we are to find the free set. But the interesting thing here, the free set is which blocks are free, but you're interested in which blocks contains data. Which blocks contains data is this manifest in memory in-memory data structure, which contains the full set of all the tables in memory. And I guess this is checkpoint reference. So and here this is already ready, and we okay. Okay. So I realized that I've skipped over a little piece of compaction, which we still have to cover. And that is the manifest log compaction. Okay, so I've said that, hey, manifest contains the full set of in-memory tables, but like obviously, like, if this is an in-memory data structure, it should start its life as on-disk data structure, because like, the replica starts, it has empty memory, it only has the data block. The data file. So we need to explain how manifest log is represented on disk. And that is like very easy. So a manifest log is represented just as log of events. Like remember, when we were writing compaction, we said, okay, so let's remove this table, let's add that table, blah, 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 blah. And manifest log is exactly this. It is just a sequence of like add table, remove table, add table, remove table, add table, add table, add table, like whatever, like maybe several removes in the row. And like, it's just like, like logs like goes, and goes. The way we store it on disk is that, well, we literally pack it into a linked list of blocks where like each block is just a sequence of events. And periodically, like, if this log contains add table full and then remove table full, then we could actually like collapse the two together. So periodically we run this like compaction process over manifest log, which also cleans up redundant entries. But okay, let's quickly look this through. So table. Okay. So let's see, like when we insert table in the manifest, then we append an entry to the manifest log. And when we append entry to the manifest log, we just where do we do this? Okay, I'm not seeing this. Oh, yeah. We just like write it to a particular in-memory block. And when this in-memory block is full, we kind of like, set its checksum and append to log block checksums. And again, important thing here is that this block also contains pointer to the previous block. So if you know the first block of a manifest log, then you know the second block, and if you know the second block, you know the third block, block, and if you know the third block, you know the fourth block, etc., etc., etc. So you only need to know the first block, and this is what our manifest log checkpoint reference is basically is. It's just like, it takes the first block of our manifest log and say, hey, this is my checkpoint reference. So again, where do we store this? Well, in super. Oh, was it replica? Okay, I'm lost again. Okay, I found myself. Okay, so in the replica, we say, okay, so we want to create a new root checkpointer. Root pointer in our grid, and kind of like this is our free set and this is our manifest reference. So this is the address and the checksum of the first block of a manifest log, and that block contains insert and remove events for tables, and if you read that log and replay it, then you reconstruct the in-memory structure of them in manifest, which tells you where are all the tables. Okay, so, and this is like super block checkpoint. And super block checkpoint is like super simple, well, it's super block, it means like super simple. It means that like, well, okay, maybe slightly less simple. So super block is like basically super block header, which is just like slab of bytes. It is how big it is. Well, I'm not seeing like how big it is, but well, kind of several kilobytes, I think. It's kind of like not super tiny, but like not like epically large, because it's just like a bunch of root pointers. So yeah, we kind of like update the stub of bytes in memory, and then we go and say that we like want to write a super block to disk, and then we are going to write this stub of bytes. And the important thing here is that we are going to write it in several copies. So you see this copy variable, and when we write the thing, then we are going to okay, let's take this slower. So how we compute this offset? We take the copy and we multiply it by the superblock size. So the copies are written one after another. And when we finish this write, we actually go and update copy to the next one. So essentially, like, to update this root pointer, we just write the superblock many times. And this means that, like, if we crash, then we read the superblock, and well, a single copy of the superblock might be corrupted, but we have written a bunch of them. So hopefully we'll find a couple of copies which are correct and which are consistent with each other, and which would be our new superblock, from which we could read the manifest log, from which we could read all the actual events, from which we could reconstruct the state of LSM tree in memory. And this allows us to sort of read operations. But superblock also contains the pointer to the block that encodes a free set. So we also read that block. We decode the free set, and now we have the free set, so we can allocate and free the blocks. So we could run compaction, and we could continue our, like, everything. So that means that we go back to replica, commit dispatch. So okay, let's replay this slightly slower. So commit dispatch. We want to commit. We have like 8,000 transfers. We want to execute it. First thing what we do is that we go and we read from disk all the data that is needed to execute the transfers. Then we synchronously execute the transfers. Then we do a bunch of compaction work. This means that we kind of like accumulate a bunch of stuff in memory, and then we start pushing the stuff from memory to disk. But this is done in a non-destructive way. This is crucial. Here, we never ever actually delete the data. We just create a new data and write it alongside. And this newly written data at this point still resides in memory. So if we, at this point, crash and restart, we completely forget about all the disk I/O we have done, and we would have to redo it from scratch. But luckily, we have be able to redo it because the prepare, which determines which work we need to do, is still in our Red Hat journal. Anyway, kind of like here, we did write a bunch of stuff to disk, and we did mark certain tables as, hey, we no longer need those tables, but this is still in memory. So when we get to the checkpoint, and like important, when we get to the checkpoint, this actually only happens like every 1,000 operations or whatnot. So it's not like we don't checkpoint after every commit. We do a bit of compaction after every commit, but the actual checkpoint is every 1,024 happens every 1,024 operations. Anyway, so okay, but I am missing all the shortcuts today. Anyway, but if we did hit the checkpoint boundary, we collect all the pointers to all our in-memory data structure as they are represented on disk, collect them into a single superblock, and write superblock to disk multiple times, and we are done. At this point, if we crash, we wouldn't have to redo all the work. And that is basically the end of the commit path. Somewhere along the lines, we probably also should reply to the client at some point. And I think this happened in the commit execute part, maybe. Maybe. Well, maybe it is an execute op. So we have reply. Oh yeah, like here, like in the middle of this whole thing, like we also hey client, like by the way, like here's a reply if you're interested in that. But that's it. And I think we are actually done here, folks. So let me try to attempt a recap of a recap. Like remember, like so we have like almost 50 episodes. So recap, kind of like condensed 50 episodes to like 2 episodes, one of which is like jumbo episodes of size 2, and now like the recap will try to condense everything further. So okay, TigerBeetle. TigerBeetle is a database for tracking financial transactions. Why this problem is hard? This problem is hard because there are a lot of financial transactions and you need to go fast. And the best way humanity knows how to go fast is to run things in parallel. But transactions are a problem which are not very amenable to parallelization because there is contention. Each transaction touches 2 accounts, and there are a few very popular accounts. So if you add logs in your database, then like this accounts kind of like will lock in the logs around those popular accounts would dominate your runtime. So the way we approach this problem with TigerBeetle is like, kind of like, this like Galaxy Brain meme. So this is kind of like, the opposite of a Galaxy Brain meme, like Flintstone Brain. We just say, okay, if like, like running stuff in parallel is hard, we're going to run stuff in a single thread. So this is like basically like big brain idea of TigerBeetle. Let's just like, take a lot of transactions and just like run them one by one on a single core, but just do this very fast. Well, how do you how can you make this very fast? Well, before you make this very fast, you like also need to make this correct, and you need to make this durable, because like if you just like use some kind of like in-memory database like Redis for this, but then like your machine crashes and restarts, you cannot get the records back because in-memory stuff is gone. Okay. Is my stream frozen? That would be super unfortunate because. Okay. No, it seems I'm still online. Okay. So yeah, you kind of like. We solved performance problem with Galaxy Brain idea of just running everything on a single thread. Like we need to solve durability problem. So the idea here is that, well, you just use more machines. You're going to have 6 machines. And these 6 machines are going to process exactly the same transaction in exactly the same order. And if like, 1 or 2 or even 3 machines out of 6 fail, then well, that's not a problem. That means that you need consensus, but consensus actually, like, it's not, consensus is like very small part of the problem. What you actually need is replication. What you actually need, like, is what we've seen today, where like you accept the request and you replicate it across 3 machines, and only proceed with committing it once you have replicated it to 3 machines. This is actually, again, because you need only 3 out of 6, you could do tail latency tolerance here. So like, you are working as the 3 fastest machines and not as the 3 slowest machines. And actually, like, this could make your system even faster than a single machine. Because, like, in a single machine, like, if it, like, for some reason, it starts to go slower, well, like, your whole system starts to go slower. But if you always pick the 3 fastest machines out of set of 3, then that might actually be faster than just a single machine which is fixed, which is like sometimes fast and sometimes slow. So anyway, that's kind of like the idea of replication. Still kind of like replication is kind of like not fast. Like you still like you need to you need to do networking round trips. So the next big idea is that we are going to optimize networking round trips. We are going to say that, hey, we will pay this network round trip, but we won't going to pay it for every single transfer. Rather, we'll pay a single network round trip for 8,000 transfers. So we pack actual transfers into big batches where each batch is 8,000, and we run replication and consensus on this granularity of a batch where we handle 8,000 transfers at the same time. That kind of like means that the overhead of consensus in terms of throughput is basically rounding error. Now how do you process 8,000 transfers? Again, kind of like the problem here is that, again, I/O. So CPU, the CPU loop for doing double entry accounting, you could optimize really, really fast. Like computers are super, super fast. Like the amount of cache CPU has is like staggering. These days CPUs have like more cache than I had like RAM back in the day. Well, maybe not kind of like that level of stupidness, but well, it kind of getting closer. But I/O kills you. But the cool thing about I/O, what we've seen today, is that although you want to execute transactions sequentially for input/output, you actually can run that in parallel, because well, you have a batch of 8,000 transfers, and nothing prevents you from like going and reading all 16,000 of accounts at the same time. So that's what we do. We just like go and read everything in parallel, and then our actual execute loop, the loop which contains double entry accounting logic, is run purely sequentially, which is very fast. That's kind of it. At some point, we also need to do journal stuff and do LSM tree and whatever. Well, no. Okay, that's kind of technical details. I realized that I forgot to mention two. I'm kind of trying to do a wrap up and actually stop these episodes, but well, gotta tell about interesting stuff. So some ideas that I have missed. One is that so you have cluster of 6 machines, and the data is naturally replicated across 6 machines. And that kind of if one machine tries to read something from disk and the read fails, it would be stupid to just say, okay, that machine is unavailable, because the data is actually replicated. So if you already replicate the data to recover from disasters, it is stupid to not use that replication to recover from local disk faults, where individual things become unavailable. So you just go and do that in your implementation. If in Targetable, if we read something from disk and the checksum doesn't match, that's a known problem. We just go and fetch the same data from a different replica. So that's one thing. And the third thing is kind of related. This is complicated. This is a lot of input output, and it's also kind of critical. It's not literally directly live critical. If Targetable has a bug, no one gets killed, but it could be pretty unfortunate, because well, this is communication, this is money in the worst case. So this is it's kind of it would be good to not have bugs. And consensus, databases, errors, it's all very, very fiddly code. So what is the plan to get that? And the plan there is to exhaustively test these through simulation testing, to not do just example-based tests, but actually exhaustively test all possible permutations of events using virtual time. So the virtual time here is a crucial thing, where when you run the test, if you run test for 10 minutes, what actually happens in terms of elapsed logical time is 10 days or 10 years. And now if you replicate that testing as we now do across 1,000 machines, where each machine has some amount of cores, then you could really ramp up the coverage of your code in terms of not in terms of the client coverage, but actually in terms of all the permutations of all the cases which could happen. But to make that happen, you really want your code to be deterministic, because if it is not deterministic, you actually wouldn't be able to reproduce that randomized testing failure, because you run it and randomness is different this time. And one of the biggest sources of non-determinism in systems behavior in general is memory allocation, because allocator is a shared resource, and the way allocator works depends on in which order you allocate stuff. And in general, allocation is totally fine for most pieces of software. But if you want to be reliable, allocation is everywhere, and allocation can easily go astray. It could easily fail at some point, or make your code slow, and to just to eliminate this class of problems at all, and just not to think about it, we also make this very kind of bold decision to, hey, let's just not just no malloc, no free, no problems. And it's kind of initially it feels hey, this is this hard. How do you do this? But it turns out that if you actually carefully not even just think, but model and compute all the upper bounds, then you could predict all the memory which you would need worst case upfront, and you could just allocate that memory and use it. For example, we were looking at the compaction code today, and there was manifest entries. And manifest entries, the amount of updates that a single compaction could do. And kind of sounds unbounded, because you don't know how many tables are going to be intersected, you don't know how many tables are going to be in the output. But actually, if you really think this through, you could actually go and say, okay, so the number of input tables is equal to the number of output tables is equal to the number of input tables, upper bound, because tables are only becoming smaller, and the number of input tables is actually bounded by the LSM growth factor due to pigeonhole principle. So that works. Similarly, when you need to read and write messages from the network, it sounds there could be many messages. But if you go into the message pool, you see that actually, hey, it is not that hard to just go and exhaustively compute all the memory requirements. Similarly, when you receive a request, how many memory do you need to process the request? Because we have a request bounded to be at most 1 megabyte, to be at most 8,000 transfers, we actually allocate memory upfront for handling exactly that worst case bound. And that, I guess, is basically it. This was the recap of Techcapital, and if you like this, then please join again at 5 p.m. UTC on Twitch. I wanted to say next week, but I think I would actually be traveling, and because we're having outside. So okay, I'm actually not sure when the next Iron Beetle will happen. But anyway, even if you miss it, it will be on YouTube. And the next time, we'll get back to what we love most. We'll get back to compaction, and after that, we'll continue chiseling at various parts of Techcapital which we haven't covered fully. Okay, thank you so much for joining with me for this today's double episode. Okay, I'm really running out of words, so let me just finish the tea, and goodbye, and see you later. you.